IIB, we're going to go ahead into chapter 16 where we start looking at different applications of the derivative. So now looking at tangents and normals, we already know something about a tangent line. So we're just going to take a general curve, and I'm just going to draw a general cubic. And we know how to find the derivative at any given point along this curve. So we could actually stop anywhere and wind up writing the equation of a tangent line. So we're just going to stop at this point here where you have an x value. And we'll say our y value is f of x, whatever this happens to be. So if I wanted to write the equation of a normal line, of a tangent line, we would wind up looking at the gradient. So we now know that the gradient is going to be the derivative at that x value. And we would also need to know at least one point. So for us, our point would be x and f of x. And we could write the equation of a line, no problem. So now we're going to introduce a new line, which is going to be the normal line. And the normal line just happens to be the perpendicular at that exact same point to the tangent line. So if I wind up drawing my tangent line, there it is. My normal line is going to be completely perpendicular. So it's going to cross at 90 degrees. At that same point that we're interested in. So for a normal line, I would still need to know my gradient, and I would still need to have a point. So I'm going to use the same point, x and f of x. But now my gradient is going to be the gradient that I would use for any perpendicular line. So instead of using f prime or f dashed, I will use the opposite reciprocal, okay, of whatever that original gradient was for the tangent line. So just as we were writing equations of perpendicular lines back in year 9 and 10, same deal here. We're just using the gradient as our, the derivative as our gradient, or the negative, the opposite reciprocal of our derivative for the normal line's gradient. So a few things to keep in mind. The first is that the definition of the normal line is it's a line that's perpendicular to the tangent line at a particular point that we're interested in. We also need to remember that the gradient of a normal line, since it is perpendicular, it's going to be opposite, so changing from positive to negative, and reciprocal, meaning it's 1 over the function, or it changes from a over b to b over a, of whatever the gradient is of your tangent line. A couple more items to keep in mind. The equation of a line in general, you guys know you can always write y equals mx plus b if you have the y-intercept and the gradient. You could also use a point and the gradient if you guys have a point, so y minus the y value equals your gradient times x minus your x value. And then remember your horizontal line, the equation is y equals, and then your b, where b is just your y-intercept. And then the same deal for your equation of a vertical line, x equals a, where a is your x-intercept. All right, so if we keep these in mind, these are kind of just basic things that we need to remember when we're writing the equation of lines, and then you'll see how they kind of apply in different ways that you can be asked what to do. So let's just take a look at this first example. We're asked to find the equation of a tangent line, and we've got 3 steps that we basically have to follow anytime we want to write the equation of a line. We need the gradient, we need a point or a y-intercept, and then you guys can actually write the equation. So what makes this a calculus question rather than a year 9 or 10 question is that to find our gradient, we're going to be using the derivative. So the derivative of f of x is 2x, and we want to specifically find the gradient at the value where x is equal to 1. So we're really just finding 2 by 1. So then our gradient winds up being 2. We have an x value, so we already know that our x value is 1. So our f of x is going to be f at 1. So 1 squared plus 1 is 2. So now I have the gradient and I have a point, which means now I can write an equation. And if I have a gradient and a point, it'll be really easy to use the point gradient form. So y minus my y value equals our gradient times x minus the x value. And then I just want to clean this up. So depending, maybe a question will ask to leave it in standard form. Maybe a question will be asking you to leave it in a certain form, but you guys know you can manipulate this as you need to. So 2x minus 2, if I move the 2 over, we really get y equals 2x. Okay, so that would be the equation of my tangent line at the point on this curve where x is equal to 1. So we're going to follow the same steps again. So step 1, let's find the gradient first. And then step 2, we'll find our point or our y-intercept. And then step 3, we'll end up writing the equation. All right, so let's just follow those same 3 again. The only difference here is that now you're being asked to find the equation of the normal line. So I'm going to start by finding the derivative. And already I want to rewrite this a bit before I start. So f of x is equal to, I'm going to rewrite this as 8 times x to the negative 1/2. That way I don't have to think about using the quotient rule. I can just use the chain rule here. So for this one, my gradient is going to be, let's see, I'll wind up with negative 4x to the negative 3/2. So if I wind up substituting in 4, I really have negative 4 divided by, so negative 3/2 would be 4 raised to the 3/2. So 3/2 as a power, remember that's the square root of 4 cubed, or 4 cubed, and then square rooted. So let's go ahead and figure out what that is. All right, so my derivative at 4 would be negative 4 divided by, the square root of 4 is 2, 2 cubed is 8, so I wind up with negative 1/2. However, the directions are asking you guys to find the equation of the normal line. So remember, the normal line means that my gradient is actually going to be opposite and reciprocal, so I'll wind up with positive 2 as my gradient. So if I just kept negative 1/2, I'd be finding the equation of the tangent line, but I want the normal line. So now I'm going to take the opposite reciprocal gradient. I also know that my x value already is 4, so if I substitute 4 into my function, I've got the square root of 4 is 2, so 8 divided by 2 is also 4. And now I can write my equation. Again, it's going to be easiest to use the y minus y1. So let's go ahead and do that, the point gradient form. So let's use y minus 4 is equal to 2 times x minus 4. And then we wind up with y minus 4 equals 2x minus 8. And y equals 2x minus 4. All right? So for the next 3 questions, I'm going to get you guys started, but we're actually going to want to finish these in class because I want you guys to think about what you're actually being asked in here in the next 3 questions. So this one says, find the equation of any horizontal tangents. So remember, if you have a horizontal tangent, so let's say I have a graph here. If I have a horizontal tangent, what is my gradient going to be of this horizontal line, right? We know that the gradient of a horizontal line is 0. So that means that really what I'm looking for is when is my gradient equal to 0, and then I'll write my equation of any lines at that point. So if I wind up thinking about my gradient, so I need to find the derivative as 3x squared minus 12, and I want to know when my gradient is equal to 0 because I want horizontal tangent lines. That means I'm going to have to substitute 0 for my gradient and figure out when that actually happens. So if I actually can figure out when that happens, what x value does that wind up happening at? If I know the x value, then how do I find the y value so I can write the equation of the line? Because remember, if we have a horizontal line, the equation of a horizontal line is going to be y equals, and then whatever that y value happens to be, the y-intercept. So go ahead and take a moment to work through this one and see if you guys can figure out what's going to happen. This next example, again, deals with tangent line, but you're being asked to find the coordinates of the points, or points, where the tangent meets the curve again. So for example, you might have a graph where you can draw a tangent line, maybe here, but it's not only going to hit at this point, but if it continues, it's going to wind up crossing the graph later on. It's not tangent at this second point, but it does wind up intersecting. So remember, if we want to find a point of intersection, we wind up setting the 2 equations equal to each other to see what point they share. So can I actually find the equation of the tangent line? And then once I have the equation of the tangent line, can I set it equal to this blue graph, whatever the original graph might have been, to see if we have a second point of intersection. All right, so start by finding the equation of the tangent line and then see what you guys can do after that. All right, guys, so for this last one, it says find the equations of the tangents to the curve, and this one you're given x squared. So if you guys are given x squared and we're trying to find the tangents to the curve from a point 2, 3, that means that the point 2, 3 is not actually on the curve, so it's sitting somewhere off the curve. And again, this is just a generic example, so you guys will have to fit it to this specific example here. But if I've got the point 2, 3 that's off the curve, and then I try to make a tangent line, technically, I could wind up making one that skims the graph this direction, or I could also make one that skims the graph this direction. So I could possibly have two different tangent lines to the curve if I'm coming from a point that's not actually on the curve itself. So think about how I could maybe set up a very generic point for these two, since I'm not exactly sure where they're going to cross. And then I can wind up writing the equation of both. All right, so you have 3 different questions asked in 3 very different ways, but all using the idea of a tangent line or a normal line. So give the 3 of these a shot, and then we'll check them when you guys come to class next time. All right, have a good night. Bye.